Hello everyone. This video is on the Knewton Alta assignment for section 9.3 called Adding and Subtracting Square Root Expressions. So in this video I'm going to be doing a preview version of this assignment, so please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same and the structure should be similar, so I'm hoping that watching me do these here helps you out in some way when you work on the assignment on your own. Alright, now on the assignment page you should have the title, the mastery bar telling you how far along you've gotten, your objectives, right, and you can see that there are 2 objectives for this assignment. Under the current objective, there should be a question related to that objective, and at the bottom of every question you should see a feedback button where you can send feedback to Knewton if you wish. You will not have this instructor cheat button. Alright, this is for instructors only. But you will have a more instruction button. If you're ever struggling with a topic or a question, try clicking on this and you'll be taken to a page with some reading or videos to study, and then you'll be given questions related to that instruction, and completing those questions is another way to progress through the assignment. Alright, so the first objective I'm looking at here is add and subtract square roots that need simplification. And you'll notice the other objective is add and subtract like square roots. These are the only kinds of square root terms we can actually add, and let me talk about that real quick before I get into this example. So like square roots. Alright, so these are square root terms that have the same radicand. They have the same radicand, and the radicand, remember, was the expression inside the square root symbol. So for example, if I was asked to add or subtract here, say I had 3 times the square root of x plus 5 times the square root of x. These would be these 2 terms. Remember, terms are separated by a addition or subtraction, addition sign here. These 2 terms are like square roots. I'll just put they are like, because you see they're both the square root of x. They both have the same radicand, the same expression inside the root. And if that's the case, you can factor that like radicand out. Now I'll factor it out on the right. I know we normally factor out on the left, but we can factor out that common square root of x, right, that like radical, that like square root that these 2 terms have. And then the remaining factor, if I remove the square root of x from both of these, we have 3 plus 5, and then you can easily combine 3 and 5 to make 8. So 8 times the square root of x is the final simplification for that first example I'm throwing at you. Alright. So it's just like combining like terms, right? If 2 terms have like square roots, you just combine the expressions outside the square roots, right? 3 plus 5 is 8, and you keep that square root the way it is. It's just like combining like terms with polynomials and junk, right? Now, an example of expressions that are not, terms that are not like square roots would be the following. Say I had 2 times the square root of 3, and I was asked to subtract, 4 times the square root of 7. These square root terms are not like, because they have different radicands. They have different expressions inside the square roots. This has a square root of 3, and this has a square root of 7. So when two radical terms or two square root terms are not like, you cannot combine them. Right? You cannot do anything with them. Right? You cannot combine, add, or subtract square root terms that are not like. Okay? Put that in a nice little bubble here. So this expression, 2 times the square root of 3 minus 4 times the square root of 7, that's how I would leave it. Alright. Now, if the square roots can be simplified, perhaps we could change them into square roots that are like. Now the square root of 3 and the square root of 7, can't be simplified any further. There are no factors of 3 or 7 that are perfect squares other than 1. But that's what this objective I'm looking at right now is about. We're asked to, again, add and subtract square roots that need simplification. So we're given an expression where the square roots are not like, but then after we simplify the square roots, and I'm assuming you've gone through sections 9.1 and 9.2, so I'm assuming you know how to simplify square roots. After we simplify the square roots, then we'll see, we're going to have some like square roots, and then we can combine like terms, right? So let me go through that here. Right, so let me write out this example. So we have 2 times the square root of 32 d to the 5th minus 7/8 times the square root of 8 d to the 5th, and then last term plus d squared times the square root of 98d. Okay. So at the moment, right, I cannot combine these. These square roots are not like. They have different radicands. This has a radicand of 32d to the 5th. This term, this square roots in this term has a radicand of 8d to the 5th. Totally different. And then this last term's radical, this last term's square root has a radicand of 98d. Also different. So I can't combine these right now. But what we're going to do first is simplify the square roots, like you saw in sections 9.1 and 9.2. So that's the first step I'm going to go through here. Alright, so I'll take these one at a time. The square root of 32 d to the 5th in the first term, I can break that up using the product property to the square root, square root times the square root. And again, I'm hoping you recall section 9.2, we would factor our radicand into a perfect square factors, times not perfect square factors. And perfect squares are things that were, raised to even powers. Anything that's raised to an even power is a perfect square because you can write it to the second power with that power to a power property of exponents. 32 is 16 times 2. Right? 16 is a perfect square. That's 4 squared. 2 is not. Right? And then d to the 5th I can break up as d to the 4th times d. Right? d to the 4th is a perfect square. That's d squared squared. Right? Anything to an even power, like I said, is a perfect square. And then d to the 1st is not. And the square root of 16d to the fourth would be 4d squared. And again, we're going to not use absolute value symbols, right? Again, I mentioned this in sections 9.1 and 9.2. For some reason, they're not having you worry about using absolute value symbols, right? So I'm not going to here either. Right? So 4d squared times the square root of 2d, right? So that is what I'm going to replace this with, and then it's going to be multiplied by 2 in a minute, right? Second term's square root was the square root of 8d to the fifth. Again, I'm going to break it up using the product property for square roots. And perfect squares times a not perfect square. 8 is 4 times 2, right? 4 is a perfect square, it's 2 squared. And then just like in the earlier one, d to the fifth I'm going to break up as d to the fourth times d. Right, d to the fourth is d squared squared. All right, so when I simplify this, the square root of 4d to the fourth would be 2d squared. And then you have times the square root of 2d. And now hopefully you're seeing what's happening here. You know, the square roots initially are not like, but once I simplify them, you see now that they're going to become like square roots. Right? They both, both of these have the square root of 2d now. Right? They have the same radicand. And then the final square root, before I actually get into simplifying the whole expression, the square root of 98d. Again, I'll break this up to a square root of a perfect square times a square root of a non-perfect square. 98 is 49 times 2. And 49 is a perfect square, right? 49 is 7 squared. And then d to the first is just, d to the first. There's nothing to do with that. There's no perfect square factor of d. And then simplifying, the square root of 49 is 7. So we have 7 times the square root of 2d. And look at that. Now all the square roots are like. Right, now all these square roots are like after simplifying. All three of them have the square root of 2d. Alright, so I'm going to pop these back into the expression. Alright, so let's keep the expression up here. So we had the first term was 2 times, and then usually when you replace something, put parentheses around it. I'm replacing the square root of 32d to the fifth with this, with 4d squared times the square root of 2d. Alright, then minus 7/8 times, and then the square root of 8d to the fifth is being replaced by this expression, 2d squared times the square root of 2d. And then finally, plus d squared times, and then the square root of 98d was 7 times the square root of 2d. Alright, like that. Alright, and now I'm going to do all the combining. Alright, we'll do some multiplication first. So 2 times 4d squared square root of 2d is 8d squared times the square root of 2d minus, and then 7/8 times 2d squared. Well, 2 goes into 8 4 times. That'd be 7/4 d squared times the square root of 2d. And then 7d squared in the last term, right? Plus 7d squared times the square root of 2d in the last term. And like I mentioned, every single one of these terms has the square root of 2d in common. So that goes at the end. Right? The square root of 2d gets factored out. And then what I'm left with is 8d squared. Well, actually, you could also factor out d squared if you want. But you have 8d squared minus 7/4 d squared plus 7d squared. And these can all go together because they're like as well. And you're going to be adding and subtracting some fractions, right? Off to the side here, 8 minus 7/4 plus 7. are the numbers we're adding. But I need a common denominator of 4 here. This would be 32 fourths minus 7 fourths plus 28 fourths, right, when you get a common denominator. And 38 minus 7 would be, 32 minus 7 would be 25. And 25 plus 28 is 53. So this is 53 fourths. 53 fourths d squared times that square root of 2d that was common. And there you go. And we are asked to leave things as an improper fraction. All right. So 53 fourths times d squared times the square root of 2d. And make sure the 2d is all in the square root. All right, and then after you submit an answer, it'll tell you if you're right or wrong, and then give you some sort of answer explanation. Please make sure to read through these answer explanations just to make sure you understand why something was right or wrong, and hopefully you can learn from your mistakes for future questions. Alright, so here's another one from that objective where the way it starts, the square roots are not like, but then after I simplify the square roots, they will be like, and then I can add or subtract. Alright, then I can combine them. Alright, so we start off with 2/7 times the square root of 108 and then plus 6 times the square root of 12. So yeah, right now I can't put these together at all. They have different radicals, not like radicals. So off to the side, I'm going to simplify the square roots. The square root of 108 and the square root of 12. 12 is the easier one. I can just say that's the square root of 4 times the square root of 3, right, which is 2 times the square root of 3. And then 108 is the square root of 36 times the square root of 3. I just knew 3 would be the radical here that I wanted, because I want these to end up being like. And 3 goes into 108 36 times, and 36 is a perfect square, right? The square root of 36 is 6. So you see how after simplifying, the square root of 108 and the square root of 12 are like radicals. They're like square roots. They both have the square root of 3 attached to them. Now they have different coefficients, sure, 6 and 2, but they still both have the square root of 3. All right, so back in the expression, we have 2/7 times, and then the square root of 108 is, 6 times the square root of 3. Plus, and then 6 times, and then the square root of 12 is 2 times the square root of 3. Right. Great, and then 2/7 times 6, that's 12/7 times the square root of 3. Plus, and then here 6 times 2 is 12. 12 times the square root of 3. And then you could, if you wanted, factor out 12 root 3. All right, both of these have 12 times the square root of 3 in common. And then what would be left over as the other factor would be 1/7 plus 1. All right, but that's 8/7. Right, 1/7 plus 7/7. That's 8/7 times 12 times the square root of 3. And 8/7 times 12, just multiply the numerators, multiply the denominators, that's 12 over 1. 8 times 12 is 96. So you have 96/7, right, times the square root of 3. And this is as simple as that's going to get. And that's what they're asking us to do, is simplify the square roots so that the terms become like square roots, and then combine those square root terms to make a single term, if possible. Right? But that's 96 sevenths times the square root of 3. And if you want to double check this, check your work, you could go to a calculator here, since this is just numbers. I got this, this is online calculator free, at desmos.com. And I punch in the first expression I was given, 2 sevenths times the square root of 108. Then plus 6 times the square root of 12. And you see the value of this is 23.7538396467, blah, 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 blah. And then put in the value of the expression I ended up with, 96 sevenths times the square root of 3, and you see it's the exact same number. Alright, so that's a way to double check my work here, with the numerical expressions anyway. So that should be good. Great. Alright, so now we're in the objective add and subtract like square roots. Well, if they're already like, this should be pretty simple. This is a much simpler objective. And I'll write this one out. Now we should of course simplify too. So here's what I mean by that. You have 9 times the square root of 9r minus 10 times the square root of 9r plus 4 times the square root of 9r. So every single one of these has the square root of 9r. Right, so you can factor that out. I put it at the end. So times the square root of 9r there, and then what you'd have left over is 9, just the coefficients being combined. 9 minus 10 plus 4. Well, that's 3. Right. So 3, we end up with 3 times the square root of 9r. But they do ask us to, totally simplify. This square root is not simplified. So that means, because there's a factor that's a perfect square. 9 is a perfect square. And you're asked to simplify the expression. Well, that's easy to fix. Off to the side here, the square root of 9r, I can just break up into the square root of 9 times the square root of r. Right, and the square root of 9 is 3. So what we have here is 3 times the square root of r, which would be 9 times the square root of r. And that's as simple as that's getting, right? The square root is simplified, all the like radicals, all the like square root terms are combined, and that's what we're asked to do, right? We're asked to simplify. So this is 9 times the square root of r. So yeah, be careful, even though they are like in the beginning, the square roots aren't simplified, right? You should still simplify the square roots at the end. Okay. So here's another one from this objective. And again, the radicals are like here, the square roots are like. So I can combine these right now, but the square root itself isn't simplified. Right. So very similar to the last example. I'm going to say I've got 6 times the square root of 8p minus 9 times the square root of 8p, right? So they both have this square root of 8p in common. I can factor that out, put it at the end. And then the factor before it would just be 6 minus 9, right? Just combine the coefficients of those square roots. Well, 6 minus 9 is negative 3, so I have negative 3 times the square root of 8p. But now I would like to simplify that square root as much as possible. Well, 8 has a perfect square factor. Then 4 is a perfect square. That goes into 8. So I can break this up into the square root of 4 times the square root of 2p. Right? 4 times 2p is 8p. And the square root of 4 is 2. Right? So this becomes 2 times the square root of 2p. So I have negative 3 times 2 times the square root of 2p. And negative 3 times 2 is negative 6. So this ends up simplifying completely to negative 6 times the square root of 2p. And that's what I'll type here. Negative 6 times the square root of 2p. And that should be good. Excellent. Alright, so another one with like square roots. Maybe. Actually, this one we're asked to simplify. See how one of them has the square root of 2a. The other one has the square root of 2b. These are not like at all. And I can't simplify them to make them like. There's no way to make these like. One has a in it, the other one has b in it. I can't just throw b in here and throw a in there. All right. So because these are not like, this is as simple as the expression will get. So I'm just going to type that expression as it is again. 3 times the square root of 2a minus 3 times the square root of 2b. And that's it. I'm not doing anything at all to that expression because those radicals are not like, and I can't see how to make them like. Okay, see, since the radicals are not like, we cannot add them. So we leave the expression as is. And here's another one exactly like that. Square root of 3c plus 9 times the square root of 5d. They have different radicands. They are not like radicals. They're not like square roots. And I cannot see how to simplify them so that they become like. One has c in it, the other one has d in it. I don't know how to fix that. So this is how I will type the answer. I'm just going to leave the expression the way it is. I can't do anything. I can't add. I can't subtract. I can't combine. They're not like square roots. So the square root of 3c, get out of there, plus 9 times the square root of 5d. And that should be enough. All right. So just pay attention to the radicands. All right, then I should just have a couple more of these where we need to simplify first and then combine. All right, and again, notice how they're saying you may assume any variables are greater than 0. That's just so you don't have to actually use the absolute value symbols, right? Remember, these square root symbols are asking you for non-negative square roots, the principal square roots, but we're not going to have to worry about absolute value symbols. All right, so this one here, we're given 5/7 times the square root of 63 n cubed minus 2 times the square root of 112 n cubed. Right? So right now, the radicals are not like. The radicands are not the same. So I can't combine these, right? But I can simplify the radicals. Now this time I'm just going to do it in the expression itself. So we have 5/7 times, and then the square root of 63n cubed I can break up to the square root of 9n squared, those are perfect squares, times the square root of 7n. Alright, that would be 63n cubed. Then minus 2 times, and then doing the same thing over here. Let's see how many times is 7 going to 112. Be 16, right? 7 times 16, 70 and 42. Yeah. So I can break up the square root of 112n cubed to the square root of 16n squared times the square root of 7n. Right, and I knew 7 wouldn't be involved because the square root of 7n is going to be the like radical, the like square root that these two terms will share after I'm done. Alright, so now I have 5/7 times the square root of 9n squared is 3n. Again, no worries about the absolute value symbols, right? They mentioned assume all the variables are greater than 0, so I don't need absolute value symbols around that. Times the square root of 7n. Then minus 2 times square root of 16n squared will be 4n. Again, no absolute value symbols. Times the square root of 7n. And now if you look at both these terms, well, they both have this n times the square root of 7n, so I'm going to put that at the end. Right, factor that out. And then the numbers that you're going to combine, 5/7 times 3 is 15/7, and then minus 8, which is 56/7. Right, 2 times 4 is 8, but 8 is 56/7. And now that I've got a common denominator, you combine the numerators. 15 minus 56 would be negative 41. So when all is said and done, this is negative 41/7 times n times the square root of 7n. Alright. Okay. Alright, and again, if you want to test it out, you could go to a calculator, just replace n with any number that's positive up here, and replace n with the same positive number down here, and you should get the same value back no matter what you plug in for n, as long as it's a positive number. But I'll leave that to you. Alright, so we end up with, after totally simplifying and combining like terms, negative 41/7 times n times the square root of 7n. Great. Alright, and I should have just one more of these based on my progress. So yeah, once again, we're given an expression. We're asked to add or subtract here, and the radicals at the moment are not like. They are not like square roots, but after simplifying, we will see that they are. Right, and then we can add them. Okay, so we have the square root of 72 plus 1/4 times the square root of 98. Again, they're not like right now. I can't put them together right now, but let's simplify the square roots, and I'll do it inside the expression here. The square root of 72 is the square root of 36 times the square root of 2. Plus, and then 1/4 times, and then the square root of 98 is the square root of 49 times the square root of 2. And so what I have is 6 times the square root of 2 in the first term, plus, and then 1/4 times 7, or 7/4 times the square root of 2 in the second term. And then both of these have the square root of 2 in common. I'll pull that out. And then all I'm adding is 6 and 7/4, so 24/4 plus 7/4, right? 6 is the same as 24/4, so I just wanted to get a common denominator. And then adding these gives me 31/4. Right, so the coefficient is 31/4, times the square root of 2. And that's a single term. That's as simple as that's getting. And then once again, I'll leave it to you to check, but if you were to enter this expression in a calculator, the one we started with, and then enter the expression I ended with, they should be the same value. So 31/4 times the square root of 2. Excellent. And that should be it for this preview version of this assignment. Like I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself, but the objectives are the same, the structure should be similar, so I'm hoping that watching me do these here helps you in some way when you work on the assignment on your own. And thank you very much for watching.